right, so we're in the last section of Unit 8. The diameter of this interval of convergence is 16. We say its radius is 8. It's centered at 0. So with this interval of convergence, its diameter is 15, centered at, since its radius of 7.5, just either subtract 7.5 from 5 or add 7.5 to negative 10. Either way, you get a center at negative 2.5. So right at the end of class on Friday, when we were looking at the interval of convergence for sine x, once we get to the end of Unit 9, you'll understand why it is, based on calculus, that sine x is this infinite series. It's an infinitely long polynomial. X minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus plus dot dot dot. So in Unit 8, you should be able to use the ratio test to find the interval of convergence. Now, if it were a geometric series, which is not, if it were in the form summation times a times r to the n, then we'd be able to find the interval of convergence by taking the absolute value of r, setting it less than or equal to 1, and no endpoint checks are required. You don't have to check the endpoints, because on the geometric series test, there's no situation in which the outcome is no conclusion. Unlike the ratio test, where greater than 1, it's diverges, less than 1 converges. If the ratio is equal to 1, then we say no conclusion. That's why we have to check the endpoints right on the boundary values. But that doesn't happen here. But whenever we have to use the ratio test to find the interval of convergence, then you have to check the endpoints. So, the interval of convergence, we have a sub n is defined as negative 1 to the n x to the 2n plus 1 over the quantity 2n plus 1 factorial. The other symbol we need to define for use in the ratio test is a sub n plus 1. Write down what you think the definition of a sub n plus 1 is. Then when you're done, compare your result to the one I have up here. I did some work in my head. When I distribute 2 across n plus 1, it becomes 2n plus 2, but 2n plus 2 plus 1 is 2n plus 3, so I just simplified that. So now, let's go and do the hard work of using the ratio test to find the interval of convergence. Instead of starting with the absolute value of r has to be less than 1 in solving for x, I'm going to start with the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. This is the starting point that is parallel in construction to the starting point for when it's a geometric series. So, with this starting point, I set out to solve for x. So a sub n plus 1 is right here. I've defined it so there's no confusion, just copy it down. Instead of dividing by a sub n, may I please have your permission to multiply by the reciprocal of a sub n instead? Thank you so much. So that's 2n plus 1 factorial upstairs, and the other part is downstairs. Okay, I'd like you to, after copying down the less than 1, see how far you can get. See if you can solve this inequality for x. Try it, see what happens. All right, let's see how you did. You make some cancellations. X to the 2n plus 3, you subtract the exponents, and you get just by the way, the negative ones cancel, leaving you with a factor of -1 upstairs. And the absolute value operator is going to disappear the -1. It's a little upsetting when a person has disappeared, but this is just a -1 that's being disappeared, so you can relax on that. When you've got the this ratio, x squared survives the cancellation process. The 2n plus 1 factorial over 2n plus 3 factorial, when those cancel, what survives the cancellation process? Yeah, we got a couple of binomials, 2n plus 3 and 2n plus 2 survive in the denominator, and I think that's it. I think everything else cancels out. So we can think about taking the limit, treating x as a constant of all things. I know it feels kind of weird to treat x as a constant, but this whole thing is, don't forget, less than 1. So, the limit as n approaches infinity. Interestingly, it's bottom heavy, and so what is the value of the limit? It's just 0. Think of x squared as maybe 14 squared. It's just a number. So it's bottom heavy. It's like taking the limit of 1 over n squared as n approaches infinity. This thing's 0. And sometimes this can be a little hard to process, but you have to ask yourself, for what values of x is 0 less than 1? All real numbers. So technically, the interval of convergence is x is an element of the set -infinity to infinity as a way to write it in set notation, or you can say all real numbers is the interval of convergence. Basically, or is the, it converges for all real numbers. So the radius is infinitely large. The radius, and it has no center, really. It's not centered anywhere. So the center technically is undefined. The radius is infinite. The interval of convergence, if you really had to write it in interval notation, would be -infinity to infinity. Any questions on our opening example? By the way, sine x, it's powerful. It came to mind when I was working with Mr. Luz from Motorola. It's like, for sine x, this procedure is going to work. Basically, what he was asking me to do was solve for t, where t is a subscript in the first throwaway term. Ended up for his application, he needed only 2 terms. He needed to keep only 2 terms from the sine x series in order to make the executives at Motorola happy. This was good enough, a good enough approximation for sine x for any particular value of x. So by the way, if he wanted to approximate sine 7, all he needed was 7 minus 7 cubed over 3 factorial. That would have been good enough. Of course, he had to generate an entire wave. He had to find, the sine of all the values between 2 particular numbers. But for any particular input, he needed only the first 2 terms. So I believe t came out to be, but basically, first 2 terms was all he needed. So t was equal to 3, k was equal to 2. First 2 terms he needed. Let's go to the next page. Yeah.
So you all learned how to derive the
Sine x is equal to this?
Yeah.
No, that's unit 9. In unit 8, I'm giving you a series like this, and we're working with them, finding intervals of convergence, but in unit 9, we're going to derive this. So we start unit 9 on Wednesday. All right, so let's take a look theoretically at some different values that you can get when you're using the ratio test, taking the limit as n approaches infinity of 2 consecutive terms. Find the center of the radius of the interval of convergence. Well, if this limit comes out to 0, that's like what just happened. 0 less than 1 is true for all values of x. And so the interval of convergence was all real numbers. And so find the center radius of the interval of convergence. So just like in the example we completed, this is, by the way, what's going through your mind. You don't have to write that down. Find the center and radius. Well, since the interval of convergence, they're not asking you to write the interval of convergence, but I'm going to write it down. Center, undefined. Radius is also, it's infinite, which means it's undefined, but it's infinitely large. What if you get 1/4? Well, guess what? 1/4, if that limit as n approaches infinity of a sub n plus 1 of a sub n, absolute value is 1/4, that's also always less than 1. Same result. Okay? What if you get the number 1? Well, turns out that 1 is less than 1 is never true. Okay? So, this will end up being one of those trivial situations where it's like x equals some number will be the only number in the interval of convergence. And so technically, you know, the center would be whatever that number is. You remember that example we did where it converged for only one value of x? I think it was on the homework, the value of x was 0. So it's like, suppose it came out to be, it only, I'll just make this up. Suppose it turned out that it only converged when x is equal to 6. Maybe the series had an x minus 6 in it, and the limit came out to 1. So then you would technically say the center is 6 and the radius is 0, if that were the case, but you just have to, it's a trivial situation. There's not a lot of intellectual challenge there. But when it comes out to something like 5/3, 5/3 is never less than 1. Just like 1 is never less than 1. So that's another thing where you have to check. Just go back to the original series. It's going to be trivial. Basically, it's going to be like there's going to be only one number in the interval of convergence. And suppose the limit comes out to be infinity or does not exist. That's, again, it's not going to be an interval of convergence. It might be one number, and you might have to look at it in a trivial fashion. But what requires more thought is when the limit comes out to be something like the absolute value of x. Okay, now we're in business, because we say the absolute value of x is less than 1. So then it's -1 is less than x is less than 1, but you'll have to check the endpoints. You'll have to look at the series when x equals -1 and do a little test for convergence. But basically it'll be centered at 0 with a radius of 1. You'll have to check the endpoints individually. If you get absolute value of x minus 5 for your limit, that's less than 1. Do the basic algebra here, where you add 5 to all three parts, you get 4 is less than x is less than 6. So what's the center of the interval of convergence? Friends?
5.
Center, 5. What's the radius? 1. Centered at 5, radius at 1. Try letter H on your own. Suppose your limit comes out to be this, using the ratio test. Find the center and the radius of the interval of convergence. Okay, so let's see how you're doing here. I'm coming up with a center at 1.5 with a radius of 0.5. Any questions on letter H? Okay, so we did do this one already. That was our first example with ratio test, find the interval of convergence. And I'm just going to shrink that one down a little bit. Am I correct in remembering that we did not yet do this example that I'm pointing to right now? Have you not yet done that one?
Correct.
Okay, would you please attempt that one right now? Please try to find the interval of convergence using the ratio test. There'll be one like that on tomorrow's test, so this will be just good practice. Already taught it, but you need more practice. Okay, just want to check in with you. As often happens, all the negative ones cancel except for one. That'll be disappeared. And the x plus 1 factor survives in the numerator. The denominator has a 2 down below. And I believe that's all that survives. So notice when you take the limit as n approaches infinity, there are no n's anymore. And therefore, the limit is simply x plus 1 over 2. Raise your hand if that's the limit that you came up with also. Yeah, there's no n's. N isn't going to infinity, so it's just the number itself. So our next move is to multiply both sides. Oh, the absolute value is still there, by the way. So x plus 1 over 2 is between negative 1 and 1. Multiply all three parts by 2 to get negative 2 is less than, x plus 1 is less than 2. And subtracting 1 from all three parts gives you negative 3 is less than x is less than 1. So the interval of convergence, the center and radius are now established. Diameter is 4. Center of radius is 2, so the center is at negative 1. So we already know the center is at negative 1 and the radius is 2. What we don't know is the interval of convergence. We've got it down to 4 possibilities. It's negative 3 to 1, where negative 3 is either inclusive or exclusive, and 1 is either inclusive or exclusive. So we need to do 2 little mini checks. These are usually not tedious. They usually come out pretty quickly. In fact, they're often known series. Either harmonic, alternating harmonic, or geometric. So you need to check them both, and it needs to be organized work. Announce to the AP graders what you're doing. You're going to check the endpoints now and do it in 2 columns. Do the check at negative 3 separately from the check at positive 1. Go back to the original series and ask yourself, what is this series when x takes on a value of negative 3? Just negative 2 to the end. So I would write this. doing some simplification in my mind, is the summation from n equals 0 to infinity of -1 to the n times, isn't -2 to the n the same thing as -1 to the n times 2 to the n? I mean, I know when x is -3, this is -2 to the n, but -2 is -1 times 2. So it's -1 to the n times 2 to the n over 2 to the n. The 2 to the n's cancel. So it's very common to get these weird things that, if you think about it, are pretty basic. It's when you multiply exponential expressions, they have the same base, you add the exponents. So you gotta ask yourself, summation n equals 0 to infinity. -1 to the 2n. What type of number is 2n every time? If n's a natural number or a counting number, what's 2n?
Even
It's an even number. What's -1 to an even number every time?
more than one.
It's +1. So this is really just a fancy way of writing 1 + 1 + 1 + 1 ... forever. What does that do? Does that converge to some value, or it diverges to infinity? So diverges at x equals -3. Notice I didn't have to use any fancy test. I didn't have to think nth term test, limit test, ratio test, root test. No, you just look at it. Usually they come out pretty nicely. Occasionally you might have to document something, but we got -1 to the n. When x equals 1, it's just 2 to the n over 2 to the n. So it's just -1 to the n. When n equals 0, we got 1 - 1 + 1 - 1. Guido, Ubaldus, 0 + 0 + 0 forever. It's just 0. It converges to 0. So that means final answer, interval of convergence, is parentheses -3, 1, square bracket. As long as x is a value from -3 exclusive to 1 inclusive, then this series will converge. So what? We're not telling, we just know it will converge to some real number there. And then last page, I think page, okay. So power series, that phrase, power series, it does have, it's a particular type. You have geometric series. Power series are in the form some function of n, x to the n. X is raised to the power n. So there's a lot of series that fit that definition. But that's what we mean by a power series. How could the first form have been more challenging? Okay, so tell you what. Interval convergence of a series is a set of independent variable values that cause a series to converge. So look at the power series for when f of x is geometric. So geometric, if f of x is geometric, bottom line is that, I summarized this already, we just use absolute value of r is less than 1. True or false? You have to check endpoints with the interval of convergence when you're using geometric. No, you don't have to use. I already mentioned that. It's just summarizing stuff I already said. If the power series for f of x is not geometric, then we find the interval of convergence by using the ratio test. Ratio. And it's glitching, so I better save my work. When finding the interval of convergence using the ratio test, you must check for interval of convergence at the endpoints of the interval. Why is this true? Just because there's no conclusion on the ratio test when it's equal to 1. So when using the ratio test, check for convergence at the endpoints of the interval. Why is this true? Because there's no conclusion. The interval of convergence for power series for f of x is the same as the interval of convergence for the power series for the derivative f prime of x and for the antiderivative of f of x dx, except possibly at the endpoints. So in Unit 9, we're going to end up taking derivatives of sigma notation and antiderivatives of sigma notation. We won't have to redo the interval of convergence, but we might have to recheck the endpoints. And by the way, if the interval of convergence has a radius of r, it's going to be in one of three types. It's going to go either -infinity to infinity, -a to a, or from 0 to 0. We've already talked about that. Clear your desks. It's time to take page 5 of the test. So Edward, if you need to go to the library, work on stuff, you can do that.